Good day everyone. In this video, let us discuss the 3.6.2 Dirac notation of Griffiths Quantum Mechanics, the third edition. Before going to discuss this topic, let us recall first the 3.6.2 and the basis in Hilbert space. Now remember that if we have this wave function, this is just the inner product of x and t is with respect to t, which means that this is the x component in expansion of the is vector in the basis of position eigenfunction. For the momentum space wave, this is the inner product of p and s, which is the p component in expansion of s vector in the basis of momentum eigenfunctions. For the energy basis, energy eigenfunction c in t, this is the inner product of n and s, which is the expansion of S in the basis of energy eigenfunction. For an operator Q acts on the alpha vector, it will provide another vector beta. So similarly, for orthogonal basis En vector, this is just, or the alpha vector is just equal to the summation of En, which is acts on the basis En. And also for beta, we have the Bn, then we have the basis En. And while En is just a summation of En that acts on the alpha, Bn summation of En that acts on the beta. The operators are represented with respect to the particular basis by their matrix element, which means that the inner product or the operator Q with Em and En, this is just equal to a matrix of Q Mn, which is describes the dimension of the matrix. So we can rewrite every time the matrix in this form, vice versa. So going back to the operator Q acts on alpha, which is equal to beta. This is just measuring the amount of the coefficients of Bn with respect to the operator. So if we substitute this beta with this value in our equation 3, and also alpha replaced with this result, then remember that if we multiply both sides by Em conjugate, then the result will be this one, which means that we can absorb this here and also Em inside the summation. So this is it. While this inner product of Em and En, and this is just the Kronecker delta of Mn. So we can replace this with this one, and take note that this summation of Bn with the Kronecker delta Mn is just equal to B, because this will strike at M. So this is the whole expression in the left side is just equal to Bn, while this one, this is just the matrix, the inner product M and N is just equal to the matrix QMN dimension. So therefore, this is just Bm, which is equal to the summation of En with the QMN. So in other words, those matrix element of Q tells us how the component transform, which means that from this equation it can be rewrite in this form, and that's by the use of the inner products. Okay, so here comes the Dirac notations of 3.6.2. Now Dirac suggested that this inner product should be split into two, which means that we have this as the bra and we have this as the cake. So the bra opens to the left while the kit opens to the right. When we see kit is just a vector whose components are in coulomb. So we have En. For alpha, we have the coefficient E1, E2 until En, and this is in coulomb, while bra is in horizontal. But these are the conjugates of the components of the vector beta. So the beta is just B1 conjugate, B2 conjugate, until Bn conjugate. So the inner product of the two, of beta and alpha, combining the two, which is the inner product of beta and alpha, is just equal to the product of the two matrix. We have this horizontal and vertical. So evaluating the two matrix, just multiply E1, B1 as conjugate, then we have respectively, then we have this result, which means this is now the expansion of the inner product of beta and alpha. So the collection of all bras constitute another vector. This is called as a dual space. So take note that the inner product of the f function and g can be converted in terms of integral, where f is the conjugate multiplied by the g function, and this is whole this expression which should be integrated with respect to x for one dimension. So therefore, we can say that the bra f is just an operator that acts on the function g, which means that the bra is actually an operator that needs a function to act on this. So therefore, if we have vector here, then we can evaluate the integral, which means that we cannot evaluate this integral unless you have the kit, which is in the which is the g, or another function. Now remember, g is a vector while the bra is just an operator, meaning the bra acts on the kit, so it requires the wave function, which is the kit. Okay, so the projector, the good thing of the separating the inner product, we have the bra and we have the kit, we can create another operator, which is the so-called projector operator, which means that if we have reversed the kit and bra, if this is kit and bra, we call this as the projector operator, meaning the projector operator can act to another function, and the role of that is to pick out the portion of any other vector that lies along this alpha vector. So if you let this projector act on a vector, we are evaluating the amount of vector that in line with this vector alpha. So for example, if we have the projector act on beta, then substituting this projector operator with this alpha, then we have this result, which means that this one is just an inner product. So take note that the inner product is a number and alpha is a vector, so therefore we can exchange its position, because this is a number and this is a vector. So this result shows that when the projector acts on the beta vector, then this is just a number multiplied by the alpha. So this is measuring the length of the beta vector in line with the alpha vector. Okay, so for the basis En, for discrete orthonormal basis, so we have this inner product, and this is a Kronecker delta. We know this every time in our previous topic. So therefore, then if you sum up all in, the sum should be equal to 1 of this projector En. This is called as identity operator. So if you take summation of the projector operator of the En basis, then we call this as identity. The answer is always equal to 1. Now this is very much useful because we can multiply 1 to any vectors that provides the same result. So identity operators are very important. So now if we let the identity operator act on the alpha, we recover the expansion of alpha in the basis of En, in the En basis. So for example, if we have alpha, then we will let the operator act on this vector. Then take note, this is 1, so nothing changed with the vector. But watch out of this, because this can be absorbed inside the summation, and this will provide this result, which means that if we allow this vector to penetrate inside the summation, then this will form an inner product. And again, this is just a number, and this is a vector, so we can interchange the position. So in other words, remember that this summation of En alpha is just equal to En. So this is the inner product of En and alpha is just equal to the coefficient of alpha with respect to n. So in other words, we have this result, and remember, the whole expression, this one is equivalent to the alpha, which means that if you let the identity operator act on the alpha, nothing changes. But remember, we can, maybe in solving problems, you can utilize some of these ideas. Okay, so similarly for the Dirac or EZ for continuous basis, Dirac orthonormalize. So the inner product of that z and z prime, this is just a delta function of z minus g prime. This is for continuous. So if you integrate that with respect to z, that operator, projector operator, the result is equal to 1. So this is now again an identity operator. Now remember that we can always rewrite the inner product that contains Hermitian operator. We can change the position of the one because this is Hermitian, so there's no difference. Okay. By the way, this we have here. So if we have this inner product of F and Q acts on F, we can change its position by this form. So because this is Hermitian, so but the ideal notation of this is operator is on the center part. So there's no such difference of this position because this is Hermitian. Now the operator takes one vector in Hilbert space and delivers another vector. So if the operator Q acts on alpha, then it takes another vector. Then the sum of the two operators is defined in this way, that if we have the two operators, the sum of the two operators that acts on a function, then this is a kind of distributive property. So we can the Q can act on the alpha added by R operator acts on and alpha also. This is for the sum. Okay. For the product, if we have the Q operator and R operator acts on the alpha, then we can regroup this that we can let the R act on alpha, then after that the result is a vector, then we let Q act on this result. Okay, then we have this power series expansion that E raised to an operator Q. It is just sometimes equal to 1 plus Q operator plus 1 over 2 Q squared 1 over 3 factorial Q cube, and so on and so forth. For 1 over 1 minus Q, this is just 1 plus Q operator Q squared plus Q cube, and so on and so forth. And for 1 over 1 plus Q operator, we have this 1 minus 1 over 2 Q squared plus 1 over 3 Q cube minus 1 over 4 Q to the fourth. Sorry, this to the fourth, then, and so on and so forth. Okay, so these are all for the Dirac notation. We are just providing the formalism of the notation for the Dirac function notation. Now let us solve one problem of the book of Griffiths, the 3.25 problem 3.25. We are given the Hamiltonian of a certain two-level system, and we have this Hamiltonian operator which has the epsilon, which is a number with dimension of the energy. So this carries energy, while the state 1 and state 2 are orthonormal bases, and the Hamiltonian operator is given on this relation, which is the epsilon multiplied by the projector of 1, or this is now the bra, or the kate and bra, minus the kate of 2 and the bra of 2, the product of 2, plus the kate of 1 multiplied by the bra of 2, and added by the kate of 2 and the bra of state 1. So all of this, we have the open parenthesis and close parenthesis multiplied by the E, and this energy, remember, is a dimension of energy. Now the question is, what is the matrix of the Hamiltonian representing the operator with respect to these bases? So meaning we will solve for the matrix operator, or the Hamiltonian operator in matrix form. So we will provide, because this is two dimensions, so we will provide the 4 elements of the Hamiltonian operator. Then after that, we will find the eigenvalues and eigenvectors as a linear combination of, the answer should be in terms of the state 1 and state 2. So for the solution, let us first solve for the first question, which is finding the Hamiltonian operator. Remember, Hamiltonian operator, this is 2 by 2 matrix, because we have two levels of system. So we have this as H11, and this is H12, H21, H22. This is row 1, column 1, row 1, column 2, row 2, column 1, and this is row 2, column 2. So we will find each of this element of the Hamiltonian, then substitute it going back to this term, or this expression, then we will provide the matrix of the Hamiltonian. So let's solve each of these elements. So let's start with okay, now this one is just equal to the inner product with the Hamiltonian in between. So therefore the H11 is just equal to the bra of 1. Then we have the Hamiltonian, and we have the Hamiltonian acts on the 1, the kate 1. So 1, 1, and we have 1, 2, and this is 2, 1, and this is 2, 2, which means that this one should be a row, and this is column. So this is row, column, row, column, and we have row, column, and we have 2 as the row and column. Okay, so let's solve first this one. So it's nice to use this one because we have this kit, in terms of kit. So we will replace the Hamiltonian, which is given on this expression, then substitute it here. So this is our Hamiltonian, and this is our bra 1, and we have the kit of 1. So next is to distribute its terms. So we have 4 terms inside the grouping symbol, so we can expect 4 terms also, and we have this bra and kit acts on the expression inside Hamiltonian. So remove the grouping symbol, and we have this result, which means that since E is constant, so we move it outside, then this one will act on this state, while this one also act on this state. So this is the first term. Okay, then again we will multiply again, or the bra acts on 2, so we have this one, and this kit 1 acts on the bra of 2, the second term. So this is the result with the E value, epsilon value. So this is minus, it's minus. Then plus, we have this act on this one, and we have E, this E, and this one act on 2. So this is act on 2. The one acts on 2, or the 2 acts on 1. Then the last term, we have this one bra, and we have the kit of 2, and this one will absorb. We have this result. So we have 1, 2, 3, 4 terms. Then let's now evaluate the inner product. Now take note that this is 1, 1. So this is Kronecker delta of 1, 1. So this is equal to 1, which means that the 2 inner product is just equal to 1 multiplied by E. So this term is just equal to E, epsilon. And this one is because this is the state 1 is state 2 orthogonal. Therefore, the inner product must be 0. So different state, the inner product should be 0. So this whole expression becomes 0, including E. And also with this one, also this is 1, but this one is 0 to 1. So this is 0, so the whole expression becomes 0. And so with the last term, this is also 0, although this is 1, but this one is 0, because they are perpendicular, orthogonal. So the inner product should be 0. So therefore this must be 0. So we have only the value of the epsilon for this first element. Then the next element, let's have this one, 1, 2, with the Hamiltonian in between. So again, substitute the Hamiltonian, the same procedure. Substitute everything here inside the inner product. Then we have this one. So then do the same. This one should be multiplied inside the Hamiltonian with the 2 state 2 in its term, and we have also E should be multiplied in its term inside. So this will be the result, similar on the first element. Again, if we evaluate the inner product, this term is 0, this term is also 0 because of this different state, and this one, this is 1, 1, 2, 2, this is just equal to 1, which means that this term is equal to epsilon, while this one is 0. So the result of the element 2, so element Hamiltonian, element 1 and 2 is also equal to epsilon. Now for the third element, 2, 1, the 2, 1 element is again the same process. Replace the Hamiltonian, then distribute the bra and the kit in its term, and also with the epsilon. So then we have this result. Okay, do it the same. This is 0 because different state, orthogonal, and this is different state. This is also 0. This one is also 0 because this is the different state. So therefore this is 0 and this is 1. So again, the result is epsilon. So the three elements are the same. Epsilon. Okay. For the last term, the 2, 2, it's 2, 2. Multiply again the same result, the same process. Replace the Hamiltonian, then distribute the bra of 2 and the kit of 2 in each term, and distribute also the epsilon in each term. So this is the result. Then this is 0 because different state. The same state, this one and the same, so meaning this is 1. So this is negative epsilon, while this one is 0, and also this is 0. So the fourth element is negative epsilon. Now substituting all the elements 1, 1, 1, 2, 2, 1, 2, 2 to the Hamiltonian, it will gives us this result. Okay, so we can take the common epsilon and we can write this as epsilon multiplied by 4 by 4 matrix 1, 1, 1, 1, 1, negative 1. So this is the answer to the problem for letter A. Now, next question is calculate the eigenvalues based on from the Hamiltonian. So take note that when the Hamiltonian acts on the psi, the wave function, it delivers an eigenvalue of energy multiplied by the psi. Okay, so therefore we will find this eigenvalue for letter C in a question. Then after that, after solving, we will solve the eigenvector. So for now, we will solve the energy of the Hamiltonian, the eigenvalues. So to do it is we need to multiply this by the identity operator, a 4 by 4, because the Hamiltonian is a 4 by 4, so we have to multiply the identity of 4 by 4. Okay, then after that, we can transpose it to the left side to make this 0. Then common factor is the psi. Then we have this, and the sum should be 0. But remember that the wave function cannot be equal to 0, which means that this one should be 0. The determinants of the matrix should be equal to 0. So we call this as a characteristic function equation. So this expression should be 0 to satisfy this condition, but remember this is not equal to 0. So in other words, we will evaluate the determinants of this matrix, the Hamiltonian minus the energy times the identity operator. So let's do it. So we will replace this with the result in letter A, then minus the eigenvalue A multiplied by the identity operator, a 4 by 4 operator or matrix, then equate to 0. Then you can multiply this eigenvalue inside this matrix. Then this is the result. Of course, this is 0, and this is E and E. Then subtract the two matrix. So it should be epsilon minus E, epsilon minus 0, epsilon minus 0, epsilon negative, epsilon minus E. So we subtract the two matrices. So we have this result as one matrix only. So this is the term first element minus first element. We have this one, and we have this 0 because 0. So we have epsilon and epsilon, and this one last element of fourth element minus this one minus E. So we have this result. So this is now the single matrix. Now we are now ready to evaluate. Take diagonal product down, positive. So then minus reverse diagonal. So this is now the result. We multiply this expression with this one. So we have this. Then minus the reverse diagonal, and it should be epsilon squared. Then we can remove this negative outside, so that we have this difference of two squares. So if we remove this one, negative, this is it. This will resolve a difference, the product of sum and difference of the same binomial. So therefore, the product, the special product, is square of epsilon and minus the square of energy. So this is the result. Now remove the grouping symbol, then we have this result, and this will becomes negative 2 epsilon square plus energy square. So this twice of this. Then we need to solve this one, so we will transpose this to the right side, becomes positive. Then we can take square root both sides to solve for the energy. Then we have this plus or minus epsilon, because we take square root of this, times square root of 2. These are the eigenvalues, two eigenvalues. So we have the eigenvalue negative or 1. Then we have this negative, considering negative. Then we have epsilon times the square root of 2. Then for energy 2, using positive, this is positive epsilon times square root of 2. Okay, so these are the answers to the problem. Then next, okay, for a while we have this result, eigenvalues. Okay, then for E, we are now to solve the eigenfunction. Okay, so this should be eigenfunctions. So for E minus, or the E1, the first eigenvalue using negative, I write this in E1 previously, but we will change that to E sub negative. And we have this negative epsilon square root of 2. Then we will substitute that to the Schrodinger equation. Hamiltonian acts on the psi, which is using the negative, and we have this this energy negative acts on times the wave function. This should be the same of this. So this should be psi of subscript of negative of this vector. So meaning we have still here. Please, this one, and we have this. Okay. So then substitute the value of this energy here, and take note that this psi using negative, we have psi 1 and psi 2, and we have psi 1 and psi 2. Then our task is to solve for, take note, to solve for this eigenvector. So kindly change this to, this is now letter C. Okay, using, this is eigenfunctions. We are to solve for the eigenfunctions. So then we have to multiply the energy on this psi. So we have this psi 1 epsilon times psi 1, epsilon times psi 2, and this should be equal to this energy multiplied by psi 1. This is our first equation, and we can create another equation by this one, psi 1 times epsilon, we have here psi 2 times negative epsilon. So this should okay, negative, then negative psi 2. So this is the second equation. We can use any of this, no, to solve for the relationship between psi 1 and psi 2. Remember, these equations are not simultaneous, so therefore we just choose any of this, then we can pick value of one variable. So using equation 1, we have this, okay, considering this one, and we will solve psi 2 in terms of psi 1. So this is the result. We'll transpose this, becomes minus, and we have this negative common. So we have square root of 2 plus 1. Then we take the common of psi 1, and this is our intention. So therefore this is psi 2. Okay, so in other words, this psi using negative value of the energy is just equal to psi 1 psi 2. Okay, but your psi 1 is what? Let us see, psi 1 is psi 1. Okay, then psi 2 is this term. So therefore this is our first eigenfunction. in terms of psi 1. Okay, so we still need to solve this one later. Okay, for now, this is the eigenfunction using the energy in negative part, negative value. So we have this result. Now next, okay, by the way, we can take out no psi 1 here. Then we have this 1 over, of course, this term. So any of these two can be used for the eigenfunction psi in the negative energy. Okay, for the next energy, we have this positive, or we assign this as E2 in the previous slide, but we will change that to positive. And of course, we use positive here. So then do it the same in this process, same process, but of course, this will becomes psi plus, and we have E plus. And substitute and this is again the same. It should be a kit, okay, a vector. Then substitute the values. Of course, we have this Hamiltonian operator, and we have the vector psi 1 and psi 2, and the same psi 1 psi 2. And this is our energy, positive. So then find the two equations by multiplying this one with that, and this one, and this should be equal to this energy multiplied by psi 1, our first equation, equation 3. Then another equation is, you can do it, this one, E times psi 1, negative epsilon times psi 2, and this should be equal to this one, energy psi 2. So we have equation 4. Again, we can choose any of that. We rather use the equation 3 to represent psi 2 and psi 1 relationship. So we have this result, and we will solve this psi 2 in terms of psi 1. So transpose this expression to the right side, then take then common factor of psi 1. So this is now our psi 2. In other words, our wave function in the positive, we have this psi 1 and psi 2, but this psi 1 psi 2 should be based on the positive energy. So this is our psi 2. So we'll replace this with this result, and we have this one. Okay, sorry, we have here psi 1. This should be quantity psi 1. Okay, then take the common out of the expression, then we have this result. So any of these two again represents the psi in the positive value of energy. So these are the two eigenfunctions, but take note, this is not yet the answer, because the question says eigenvectors in terms of its state 1 and state 2. So meaning we need to normalize these two equations, two functions, and we will solve psi 1. In other words, we will solve psi 1 here in positive, solve psi 1 here in positive eigenvalue. So the next step is to normalize. So normalizing our negative psi negative vector, then this is our psi. Take note. So we will to normalize is just square this expression, the x value, and this one is square, then add the two, then the square root, the answer should be 1, because we are normalizing. So therefore you can use any of this, but I think it's good to use this one. So all you need to do is to square this, then square this, okay, then not square root, square, then equal to 1. Okay, then combine this is square, so we have to, the term should be squared. Then this is a binomial, no? We can if you square this will becomes plus, so this is plus. Then again we can square this binomial, then we have this result. So square the first, twice the first and second, square the last, and this is the result, the square of binomial. So therefore this will becomes 2 and 2, 4, so 4, and this is 2 square root of 2. So we can take the common of 2 here, then we have 2 square root of 2. Then after that, divide both sides by these expressions, leaving psi 1 square. So we have that, then take square root. Okay, so taking square root, then of course this is plus or minus, and we have 1 minus square root of 2, which is this one, and this is 2 plus square root of 2, then take square root. So this is our psi 1 normalized. Okay, then of course substitute this psi 1 to the equation, this one. So we have this result. This is our eigenfunction for the eigenvalue negative. So in terms of the basis, this is now the matrix. In terms of the basis expansion, we have this 1 times acts on the state 1, and this is this component acts on state 2, so it should be plus. So therefore this is the final answer for the first eigenvector using negative eigenvalue. So let's do it the same for the next. So normalizing the positive psi, normalizing this one. Of course this is the same. Then again the same, square this one plus square of this, then equal to 1 to normalize, and this will becomes again square of this, and this is square of binomial, and this is also square of psi. We can take out of this square of psi 1, and we have this 1 for that, and plus this one is a square of binomial. So square the first, twice the first and second, square the last for the square binomial. So we have this result. Square the first, twice the first and second, and we have this square the last. Then added by 1. So this is 1 plus 1, 2, plus 4, still we have 4. Common factor 2, we can take it out. And this is 2 minus square root of 1, square root of 2. Then solving for psi 1. So divide both sides by this quantity, then take square root, and we have this result. Okay? Then substitute this psi 1 here. Then we have this result, and express this matrix in the expansion of the kit 1 and or the basis 1 and basis 2. So we have this 1 times state 1 plus this coefficient times the state 2. So this is the, or this is, by the way, sorry to, this should be plus, sorry. This should be plus. This is another state. This is for the positive what's that? Positive eigenvalue of energy. So this is now our eigenfunction using the positive eigenvalue of energy. Okay, so these are all for this problem. So thank you for listening.